So chapter 2 is about derivatives. Derivatives. Let's see if we can work out. So basically, derivatives are what we actually care about. Okay, derivatives are the slope of a tangent line, which is one of the main uses of calculus. 2.1 we're going to do today. That's the definition of derivatives. It's telling you exactly what a derivative is. 2.2, 2.3, 2.4 are all going to be rules that you're going to have to learn and be able to use to take the derivatives. Um, 2.5 and 2.6 are kind of applications. 2.5 is about something called implicit differentiation. So it's the derivative applied in a slightly broader context. And then 2.6 are related rates problems, which are word problems. Most of this chapter, what we're going to be doing is talking about what a derivative is and how we find it for any given function.
Derivative is a slope of a tangent line, you said?
Yeah, I'm gonna define it very specifically when we get into 2.1. But yes, the idea is that the derivative of a function is in some way going to give you the slope of that function. So I'll get very specific. Derivatives. So the derivative in tangent lines is kind of the tag, the title here. So it's actually a little bit difficult to define what a tangent line is. It's a little bit difficult to define what a tangent line is. So what you might think, what you might have heard, what I might have even told you, is that a tangent line to a curve, so here's a curve, here's a circle. Here's a curve. The tangent line to a curve is going to be a line that just touches the curve at one point. So for example, for this circle that I drew here, the tangent line at this point will look something like this. Just goes right through that point, touches the curve. And our whole goal is to figure out how we can find the equation, or the slope of this tangent line, and then the equation of this tangent line. But you got to be a little careful. So, for example, if I give you, well, here's another curve that has an obvious tangent line. Say I want the tangent line at the top of this upside down parabola. What do you think that's going to look like? Just a horizontal line. Right? If you want to touch this and just barely raise the function and keep going, you have to draw a horizontal line. Right? If you tilt it a little bit, then it's going to hit the function more than once. At least that's good. Now the place that gets tricky is in maybe a graph like, let's do x cubed. All right, so there's a decent shape snake for x cubed. And I want to find the tangent line at 0, 0. What do you think that's going to look like? It's actually horizontal. It's It's actually horizontal. Right? What you want to kind of think of is imagine taking tangent lines on your way to 0 from the left. Right? Or even taking secant lines. Take this secant line through this point and this point. Secant line means it goes through 2 points. There's a secant line. Take another secant line with a point a little closer. Looks like this. Take another secant line with a point a little closer. As you get closer and closer to 0, 0 with that extra point, your secant line ends up being horizontal. So the tangent line at 0, 0 is horizontal, but that's a little counterintuitive because it goes through the graph. It does. But going through the graph is kind of different in these cases, right? You could actually have, let me give you one more example. So maybe I give you something like this guy here. Perfectly good function. And if I pick on the tangent line at this point here, it's going to have to go under the graph just to kiss it there at one point. But as you can see, because of the shape of the graph later on, it actually goes through and hits the graph again. So this is the tangent line at this point, but it touches the graph twice. So my point is that the definition of a tangent line is a little vague, because it's not only that it touches the graph once, because this one touches it twice, and it's not only that it grazes the graph, like this guy actually goes right through it. So you need what you need to do to specifically define a tangent line is talk about secant lines and the limit of secant.
It's a line and it goes forever.
Tangent lines?
Yeah.
Tangent lines always go forever.
So, I like read part of the book. It said on a closed interval A to B. Is that what it means? Like you pick like 2 short points next to it?
It depends on the context, but if you say a closed interval, if you say an x value on a closed interval A to B, then A and B would be on one side, B would be on the other side, and your x value would be in between.
That's how it only touched once.
Yeah, so yeah, you could fix this definition up by saying the tangent line is going to be a line that only touches your curve once on a small enough interval. That would work. So let me kind of take you through the setup for finding the tangent line, and then we can talk a little bit more specifically about what it is. So example. So let f of x equal x squared, right, our favorite function. First thing I want you to do, find and simplify f of x plus delta x minus f of x divided by delta x. So in this context, delta x itself is supposed to be a variable, and it represents a small change in x. So in your head, you want to think of this delta x as meaning a small change in x. In general, when you see delta, right, that triangle, in math, it represents a change. So how would I calculate what this algebraic quantity is for this function?
X plus delta squared.
Yeah, you have to first figure out what x plus delta x equals when you plug it into f. So you have to figure out first what this guy is. So I'll do that right here. F of x plus delta x equals, well, this means take this quantity and plug it into your function. And then this is where your algebra has to take over. If you're squaring a sum, you have to FOIL. So you would write this as x plus delta x times x plus delta x. And then square this out, or FOIL this out. Yeah, so you'll get x times x is x squared, x times delta x, and then x times delta x again.
2x delta x.
So you get 2x delta x. And then delta x times delta x, delta x.
Just like that.
So overall, now if we go back to what I care about, f of x plus delta x minus f of x all over delta x, in place of this guy, I put this guy. In place of this guy, in place of f of x, I put f of x, which is right here. And then delta x variable just sits there. So altogether, I'll get x squared plus 2x delta x plus delta x squared from this first portion minus the function, which is x squared. And if you do if you do this right, a lot of things should cancel. Well, in this case, only one thing does, but that's all we need. The x squared is canceled. So you're left with 2x delta x plus delta x squared over delta x, which you can simplify by factor out delta x and then cancel. So delta x comes out in front. You're left with 2x plus delta x over delta x. These cancel. So at the end of the day, this quantity is just equal to 2x plus delta x. All the other. Now, whatever, that's just algebra. We need to know how to do it, and you're going to be doing this a lot in this section, but who cares? What does this tell you? What does this quantity tell you about this function?
It's the slope.
It's the slope of a particular line.
That's the difference quotient, right?
It is the difference quotient, and the difference quotient represents the slope of the secant line through certain x values. So my function originally is this guy, x squared. When you see this x and this delta x, basically what that's telling you is pick any x value you want in the domain of your function. Delta x is going to represent a small change in x, so it's a small quantity that you're going to consider adding to x. So maybe delta x is just this little portion right here. Maybe that's delta x. And then that brings you to x plus delta x. So what the difference quotient is telling you, which is what this represents, right? This is called the difference quotient. What it's telling you is that if you take first of all, f of x plus delta x, which is up here. Right, this is f of x plus delta x. And then you, oh, no,
Wait,
that's f of x. My bad. That's just f of x, right? This one is f of x plus delta x. So if you take those two x values and plug them into your function, and then you divide by delta x, what does it look like you're getting?
Secant line?
The slope of the secant line. Because the difference in these two is your change in y. That's how much y changes. Delta x is how much x changes. So if you take this line here, and you calculate the slope, it is the same thing as taking f of x plus delta x minus f of x. Okay, but I don't actually, so that is the secant line because it goes through 2 points. Okay? It goes through 2 separate points and it cuts right through your function. The tangent line, the idea that we're talking about for a tangent line is supposed to be a line that just kisses your function, just brushes your function at one point. Okay? So if I wanted to instead talk about the slope of a tangent line, I would want to just touch my function at this single point. So what I'm going to have to do is bring my second point, right, lower my delta x. Instead of making delta x this much, maybe make delta x a little less. And then draw a secant line. And then make delta x a little less again. And then draw a secant line. And then make delta x a little less again. And then make delta x a little less again. Until eventually delta x falls right on, goes to 0, and your point falls right on top of your original point. And that'll give you this line, where it just cuts through once. So what I'm saying is this guy gives you the slope of any secant line through x and delta x. But if I want the slope of a tangent line, what am I going to have to do to this?
The limit,
As?
delta x goes to 0.
Right, I want to take delta x to 0. If I take delta x to 0, my points will get closer and closer and closer until eventually it's just one point that my line is going to. So this will give you the slope of the secant line through x and delta x. But if you do, so let's do b, let's calculate the limit as delta x goes to 0 of this quantity, of this difference quotient. So the limit as delta x goes to 0 of this difference quotient, well, I did a bunch of algebra on this, and I learned that the difference quotient is just equal to this. So this limit is equal to the limit as x goes to 0 of 2x plus delta x. Like this guy. But as delta x goes to 0, this is just equal to what? This 2x is representing the slope of the tangent line at any x value. And one way to technically define a tangent line is to say it's the limit of the secant lines as you take the 2 points, but the 2 points on the secant line and make them closer to one another. Okay, so a tangent line is a limit of a bunch of different secant lines. This guy had a bunch of different lines going through it. And eventually, those lines were ending up at the tangent. How come it still has an x in it? Right? For example, the slope of this line should be constant, like 5 or 4 or something. How come there's an x here?
Slope's going changes.
Yeah, the slope changes depending on which x value you pick, right? So for example, if I wanted the slope of the tangent line through x equals -3, that would be this line here. What would that slope be? -6. Right, you just plug it in. This slope has to be 2 times -3. So this x, if you plug in a value for it, that will give you the specific slope of the tangent line at that x. One other question. When I evaluated this limit, why do I have to do all this algebra? Why couldn't I just plug in, why couldn't I just plug in 0 immediately for delta x? Why can't you plug in 0 right here? Yeah, if you put in 0 for delta x, the top becomes f of x minus f of x, which is 0. And if you put in 0 on the bottom, you get 0. So when you start doing the slope of the tangent line, the limit is always going to start off as 0 over 0. And then you have to do some algebra simplification to make it look like something you can evaluate. Which is one of the reasons we did chapter 1, so you know how to evaluate these limits for tangent lines. Let me give you the gist here, what we actually care about, where this is going. This is the whole point of this section, or this chapter for that matter. The derivative of f at x given by the formula f prime of x. So this is this is one notation for the derivative. I'll talk about this in a second. Okay, so this is some new notation, but the derivative is some new function, and it's notated sometimes by f prime. And the way you find it is to do the limit as delta x goes to 0 of the difference quotient. So when you see f prime, that means derivative, and the way you calculate it, at least for this section, is to do the limit of the difference. Delta x goes to 0. So I'll do like as many examples as I have time for, okay, but this is the definition. A couple of notes about this. This function, f, this is a new function. F prime of x is another function. All right, come back over here. When we did this limit as delta x goes to 0, we got 2x, a whole new function. And the way 2x is related to x squared is that 2x gives you the slope of the tangent line at any point. Okay, but there are two new functions, or there's one new function. It's a totally new function, not just a single value. Okay, so the derivative is a function. There are several notations for derivative, which confuses students to no end. Depending on which book you use, which teacher you have to deal with, the mood that I'm in, you will see a different notation. Okay? So one notation is this prime notation. Right? So all of these mean derivative. Okay, so f prime is what we just saw. You could also see y prime, right? If I use y instead of f for my function, y prime means the derivative. You could also see something like dy dx. The idea here is that a derivative is a change in y over a change in x. So one notation is, say, dy dx, which means the infinitesimally small change in y over the infinitesimally small change in x. So I'll use this sometimes. Again, if I like f instead of y, you might see df dx. Or, if it's necessary, or it helps me a little, or it helps the author a little, you might just see d divided by dx. And then it'll be applied to some function, like this. So really, when you start seeing these d's, derivative, right? And when you see primes, derivative. Right? These all mean take the derivative of your function. I would say I'm going to try to stick to one, but I know, first of all, I won't, and second of all, the book will use several different ones, and third of all, your next teacher might use several different ones. Certainly, if you're in physics, you'll see these a lot more than primes. So I'm just going to try to get you used to all of them. All right. So one other kind of notation thing, or technicality here. We say a function is differentiable. So function is differentiable at x equals c. So at some random x value, if its derivative exists. If f prime of c exists. So the derivative of your function evaluated at c. So for example, x squared. Go back to this function here, y equals x squared. Where is this function differentiable? What does that question even mean? So where is x squared differentiable means where does the derivative exist? Well, the derivative, y prime, is equal to 2x. That's what we just calculated. So where is this function differentiable? Where does y prime exist? Everywhere. There's no problems. So when we ask about where a function is differentiable, we're saying take the derivative and figure out where, we're asking for the domain of the derivative. Okay. Let's do some examples. Oh, I guess there's one more note in case I didn't make it abundantly clear. F prime of C means, so as far as like physical interpretation, right, like what you should think when you see f prime of a number, this means the slope of the tangent line to the function at x equals c. Slope of, you can even say it like this, it's just the slope of the function at x equals c. So use the definition to find the derivative of each function. Start you off with, I guess, the easiest possible function I'm going to ask you to find the derivative of. Trick you off, we'll see. 5.
1.
F of x, oh,
Zero.
my heart hurts.
0.
0! If I know anything about what a derivative means, the derivative of this guy should always be 0. Why?
Because it's a horizontal.
It's a horizontal line. And what's the slope of a horizontal line?
0.
But we're going to use the definition. This is the definition. We're going to show it. So if I want to use the definition to find the derivative of this function, I would say f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. This is the definition of derivative. And if instructions say use the definition, this is what you see. But what are the things in this case? What is f of x plus delta x? 5. It's always 5. I don't care what you plug into f, you're going to get out 5. And what's f of x? 5. I don't care what you plug in, you get out 5. So altogether, this limit just becomes, yeah,
Or 0.
0 over delta x. Thank you, yeah. So this will be 5 minus 5 over delta x is 0 over anything, still 0. So 0 over delta x, that's always 0 no matter what. There's no trick to that. So our intuition as far as slope goes told us the derivative should be 0. Our calculation agrees. F prime of x is equal to easy enough? Oh. Yes, question.
When you plug in 5 for the first one, is it 5 plus delta x? Or is it just 5?
When I plug in, well, first of all, I'm plugging in x plus delta x.
Right.
So when I plug in x plus delta x here,
Oh, gotcha.
it's still just 5, yeah. Because there's nothing to plug in on the other
So
side.
that's two different functions, right?
This
So-
and this,
Right, f of x equals 5, but why is f of x plus delta x equal 5?
well, let's see. What's f of, so focusing on this, what's f of 1?
5.
5, right?
Okay.
What's f of 2? 5. What's f of pi?
5.
5. So, no matter what I plug in, it's 5. Even if I plug in this, it's still 5.
Right.
So these aren't actually two different functions, they're the same function evaluated at different places. But since this is always the same, no matter where you evaluate it, you get to. Now this is different than, say this guy. So same problem. I want to find the derivative using the definition on this guy. You should still have an intuition. What do you think the derivative is at 5? 5. Because the slope of this line is 5 and the derivative means slope, so well, let's calculate it. So if I want to find the derivative of this function, I need to do the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So in this case, what's f of x plus delta x? And this gets plugged in here. Right, that's how the difference quotient works. You plug x plus delta x in for your x. So I'm going to write 5 times x plus delta x plus 4. For this first portion, you first plug this in here and then write the result down. This guy is f of x plus 4. And then f of x, you just recopy this, but be careful, don't mess your signs up. Right, you have to subtract the entire function f of x, so you do this. Minus 5x plus 4 in parentheses. So that negative goes to everything. So here's minus f of x. Now you can't just plug in delta x equals 0 because you get 0 over 0. So you do the algebra and make sure everything cancels, or at least enough cancels. So on top, I'll probably distribute out that 5 and distribute out that negative. 5x plus 5 delta x plus 4 minus 5x minus 4. Now we're cooking. 5x is canceled, 4 is canceled. All we have left is 5, right? When all the dust settles, all is said and done, the delta x's are going to cancel. So if the limit is delta x goes to 0, or 5, g equals 5. This is what we call it. So we know things.
Like if it was harder, can you push it through? Like what you're saying with the limits? So like how the 4 would just be 0 on 5x plus 4 at the top.
No, really, until you get rid of this delta x in the bottom, we can't push anything through. Because at first, when you evaluate this, it's 0 over 0, which means your limit laws don't apply. You don't know if it's defined.
Well, if you did, like for the first one, if it was, took the derivative of 5x and then added the derivative of 4.
Yeah, so it'll turn out that, like at this point right here, we could separate this into 2 different fractions. And then one of the fractions gives you the derivative of 5x, and one of the fractions gives you the derivative of 4. But in general, you want to avoid putting the limit in until you're sure that it's going to not give you 0 over 0. Why do you want to put it in? What advantage is that?
Well, because if you could do, you know, 5, if you like just didn't care about the 4, because if you could split it, then you wouldn't have to even have the 4 in the beginning.
Yeah, I guess the 4 goes away anyway.
I was just curious, like if it went got harder, if you could do that.
I wouldn't suggest. I mean, yeah. I mean, you can show that the derivative of a constant is 0, and you will. Right? And you can show that this limit is going to be the same as if you split it up. If you just did the derivative of this and the derivative of this, but I wouldn't start breaking things apart in here. Because you don't know whether it exists until you cancel out that delta x, so it doesn't necessarily mean it's true. Let me give you a slightly harder one, we're still not too difficult. So this was my derivative here. Actually, let me go back here. This was f prime of x equals 5. So what I want to show you real quick before I do this next problem, which I'll do, what do the graphs of f of x and f prime of x look like here? You know? What's the graph of f of x?
Just a line.
It's a line going through 4, right? 1, 2, 3, 4. Slope 5. So it goes 1, 2, 3, 4, 5 over 1. So it'll be like 4, 0, 5 over 1. So this is more. This is f of x equals 5x plus. And what is the graph of the derivative function? The derivative function, f prime, is just 5. No matter what x is, the derivative is 5. So what kind of line is this?
Horizontal line.
So what's the relationship? Well, if I pick any point on this graph, The y value of that point is the slope of this function. Right, if I pick this point over here, x equals -3, and I go up to my y value, which is 5, that'll give me the slope of this function at -3. So every y value on here gives you a slope on this guy. So just keep that in mind. Keep that in mind for when it gets more complicated. So we'll give you this guy, x squared plus 3x plus 1. So if I want to find my derivative for this, I'm going to use a different notation. So it uses df dx, the derivative of this function with respect to x, equals. I do the same limit. I'm always doing the same limit when I have to do the derivative. Again and again and again and again, and then 5 more times. But what happens in this case when you plug x plus delta x in? What do you get?
Or delta.
So you're going to have to take this whole thing and plug it in here. You're going to have to take this whole thing and plug it in here. This guy gets plugged in here and here. So for f of x plus delta x, you'll get x plus delta x squared plus 3x plus delta x plus 1. This is f of x plus delta x. Then I have to subtract from that f of x. So minus the whole original function. All over delta x. Oops. And if you do this right, your delta x in the bottom should end up canceling. So we've got to actually do some algebra here. What happens with this x plus delta x squared?
X squared plus 2x delta x.
Yeah, FOIL it out. You have to do x plus delta x times x plus delta x. When you do that, you FOIL, and you end up with limit as delta x goes to 0. This guy becomes x squared plus 2x delta x plus delta x squared. Right, we just did that. Then you distribute out this 3. Then you add the 1. Then you distribute out this negative, subtract all of this. If you're bad at algebra, this section's your nightmare. You never get through any of these. I hope you're not bad at algebra. Things should always cancel nicely. Right? 3x positive, 3x negative. X squared positive, x squared negative. 1 positive, 1 negative. So you get limit as delta x goes to 0. 2x delta x plus delta x squared plus 3 delta x. Looks like that's it. Over. So all you're left with are delta x's on top, right? Every term has a delta x. So then how do you finish this? Factor x. You get a delta x out front, 2x plus delta x plus 3. These cancel. Once your delta x in the bottom cancels, then you can just plug your 0 in, right? Distribute the limit. Delta x goes to 0 isn't going to matter here, but as delta x goes to 0, this guy becomes 0. So what do you end up with? 2x plus 3. So for f of x equals x squared plus 3x plus 1, the derivative, which I'm calling df dx, just to get you used to seeing it, is 2x plus 3. I say use the definition of derivative. This is what I want to see. And if you don't do this, I don't want it. Later, when you grow up, and you prove to me you do this, it will give you, the book will give you, it will give you nice tricks to do it much nicer. So 2 things. One, I'm going to graph these real well. I don't know about graph, but I'll give you an idea of what these look like. What's this function look? What kind of function is this? Parabola, right? It's a quadratic function. It's got an x squared. So this guy's a parabola. So it looks something like one opening upward. Something like this, maybe. I don't know what's b squared minus 4ac. It might actually hit the x-axis, but it doesn't really matter. This is your function. What though does the derivative look like, and what does that mean? Right? What's this guy look like? It's a line, right? Going through 3 with slope 2. So you go through 3 on the y-axis up 2 over 1. So this is your derivative function. This point right here is actually very interesting because your derivative is changing from a positive y value to a negative y value. You know what? Can you solve for this point? What's the x-intercept of this line? If you set y equal to 0 on your line, if you set this side equal to 0 and you solve for x, what do you get? Negative 3 halves. So this point right here is negative 3 halves. What happens on the graph of the original function at that x value? There's, well, one way to interpret it is that this is going to be a horizontal tangent line because you have to have, since this represents the slope of your function, you have to have slope 0 at x equals negative 3 halves. So at x equals negative 3 halves, you have to have a tangent line that has slope 0 because that's what's happening on this derivative function. Another way of looking at it is that x equals negative 3 halves, this line goes from positive to negative. So the slope of your tangent line up here should be positive on one side and negative on the other side. So this whole portion of the graph, the derivative is positive. Which means up here on your original function, the slope is positive. So if you look at any x value that's bigger than negative 3 halves over here, and you draw a tangent line, you're going to get a positive slope. Whereas if you look at any x value that's less than negative 3 halves, like over here, and you draw a tangent line, you're going to get a negative slope. That's what this is telling you. Negative. So in this portion, your derivative is negative, which is why you're getting negative slopes on the left over here. I'm just getting you used to this idea that the y values on here represent the slopes up here.
Are derivatives always one exponent less than the function? Because
If that question makes sense, yes. Right, because not all functions have, no, your question does make sense. What I'm saying is, if I give you a function that's a polynomial, you can say that. But if I give you like sine x, cos x,
Okay.
you know what I mean, then you can't make that characterization. Yes, and what we will learn in the next section is the power rule, which tells you actually to find the derivative, you can just swing this exponent down into a constant in front and subtract 1 from the power. And that gives you the derivative. So yes, this pattern that you're seeing where the derivative of a polynomial drops the degree of the polynomial by 1 is right. That's correct. Let me give you one that's not a polynomial. So our last example of using this definition. Let's take f of x, our function, we're going to call it y. Let's take y equal to root x, and we want to find the derivative. So, let me use y prime this time for my notation. So y prime means the derivative of this function. And the definition tells me I need to take the limit as delta x goes to 0. Normally we would say f of x plus delta x. We'd say y of x plus delta x minus y of x over delta x. That's our function's name. How do I calculate y of x plus delta x, or f of x plus delta x? Whoa, calm down there, people.
Oh, I'm sorry.
You're flying by me right now. I need to put my seatbelt on, man. So we need to plug this stuff in first, right? When we plug x plus delta x into the square root function, we get this. So that's the first portion of my difference quotient. Then I subtract the same thing again. And then I divide by delta. Now to evaluate this limit, you absolutely have to multiply by the conjugate. Right? Because when you plug delta x in, you're going to get, if you plug in 0 for delta x, you're going to get 0 over 0. So you're dealing with 0 over 0 limit when you have square roots. Our best hope is to multiply by the conjugate. So to actually evaluate this limit, I hit top and bottom by the conjugate. What's the conjugate here?
Square root of x plus delta x plus square root of x.
Right, so you change the sign in the middle. Keep the square root of x plus delta x, keep the square root of x, but change it to plus in the middle. And do the same thing on bottom. Square root of x plus delta x plus root x. And just like before, I am going to want to multiply on the top to help me get rid of these roots. I'm not going to multiply on the bottom in hopes that things cancel. So on top, maybe we can do this without a lot of headache. What happens when you multiply these binomials?
X plus.
Yeah, so when you do root x plus delta x times root x plus delta x, that gives you x plus delta x. And when you do root x times root x, that gives you minus x. Right? Minus x.
Negative x squared? I'm sorry, in the very end.
Yeah, so these guys give you x plus delta x. These guys give you minus x, because the root goes away. And then the middle terms drop out. When you do, let's see, we have to do this guy times this guy, and then this guy times this guy. Those will cancel because one they'll be the same exact thing, but one will be positive and one will be negative. So this is what you like. Then don't do squat to the bottom. Leave it exactly as it is. And what happens here? Yeah, things cancel really nicely, right? This x and this negative x go to 0. Right? They equal 0 when you collect them. So you just have a delta x left on top, which is going to cancel with the delta x left on bottom. So this guy and this guy leave you with a 1 on top. So you have to calculate the limit as delta x goes to 0 of 1 over root x plus delta x plus root x. But it doesn't, there's a delta x on bottom, but it doesn't make the bottom 0 anymore. Right? If you plug this in, this guy goes away, but you still have stuff left over. So you will plug in 0 for delta x here, since it doesn't make the whole bottom 0. And then you will get 1 over root x plus root x, which is 2 root x. That's what your derivative function is.
Are we not supposed to have a square root in the denominator?
Okay. Worry about that right now. You're right. You could multiply top and bottom by root x, but it's not important.
Oh. There's some thinking.
Absolutely. All right. What you have to be careful of here, though, quickly, if you plug in 0 to the derivative, what do you get? 1 over 0, which is undefined. Right? So the derivative is not defined at 0 in this for this particular function. Everywhere else it's fine. You can plug in 1, 2, 7 pi, fine. But at 0 or even negative x values, you're not defined. What does that mean?
You have to write it on there.
Why do you think that is? Let me rephrase. Why do you think it is the derivative is not defined at 0? Yeah, what's root x look like?
0.
It's this rainbow, right? It's half rainbow. So now, if you want to try and find the tangent line, the slope of the tangent line, the way we did it was we took points all around here. And then took the limit of the slope of the secant lines. Right? So you can take the limit of the slope of the secant lines from one side, but you have no points on the other side to take the slope of. So just like how the regular limit isn't defined as you go to 0, the limit of the difference quotient isn't going to be defined as you go to 0 because there's nothing on the left. So this derivative is not defined at 0 because there's nothing on the left to take it. And also it goes to infinity anyways. You'd be screwed. You can work it somewhere. But sometimes the derivative is undefined, and that just means you don't have a slope at that point. You don't have a well-defined slope. But let me do one more. Different. Sketch a possible graph for the derivative of the function. So I'm going to give you a function and I want you to sketch a possible graph for the derivative. Now it doesn't have to be, you won't be able to make it exact because I won't give you enough information. But you can kind of give me a big idea. Here's A. The function is going to look like this line. And I want a possible graph of f prime, the derivative. So how do you think I can analyze this to get the graph of the derivative? Without having the formula, right? I don't actually want to do a difference quotient. I don't actually want to use any equations. I just want to think what the derivative means.
That it's the slope of.
So the derivative is the slope at any point. And this is a line, so the slope is always the same. Now, so what that's saying is that the y values of the derivative are always going to be the same. Would it make sense for me to draw this as my derivative? Why would this not make sense? Because the slope here is negative. Right? Which means that all the y values of my derivative have to be negative. But if you draw me a line down here, then you're okay. Any horizontal line would work as a possible derivative function. Because I don't know exactly what the slope is. But I do know the slope is negative. So I know that this guy is some y equals some negative number. This, here's F. Wow. What's the derivative going to look like in y? Well, yeah, that's x squared. You don't know that's exactly x squared. So tell me it in terms of graphs. So
We're gonna go through the middle.
right, so it's okay, so you know a couple things. You have a horizontal tangent line right here, right?
Mm-hmm.
Which means that your derivative has to equal 0 at this x value. Right? Now over here, m is positive. And even over here, it's more positive. Right? So it's going up. Your y values are getting bigger and bigger on this side. Over here, your m's are negative. And over here, it's even more negative. So what that means is you're going to go down and keep going down forever. The y values are going to get more and more negative because the slope's getting more and more negative as you go to the left. This is F prime. So what you want to do to graph, in general, don't try and think of an equation, because I could give you some funky graph that isn't going to, you're not going to be able to find an equation for. In order to graph the derivative, you just think of what the slope equals at every point. Here's your function f of x. I want to know what the graph of the derivative is.
We get graph.
It's actually not a graph. So what kind of analysis can we do here? We're graphing a derivative, we want to talk about slope. So I want to look at, for example, if I take a point way out here, what's my slope looking like? Almost 0, right? Because I almost have a horizontal tangent line as I get further and further out. So m over here is almost 0. But as I get closer in, it's getting more positive. And as I get even closer to 0, it's getting more steep. Put 2 plus signs. More positive. And actually at 0, the way the trend is going, it's going to be vertical. It's going to get huge. The way this is ramping up, my slope is getting bigger and bigger. And then on the other side, it's going to be very positive right here. But then as you get further and further away from the origin, it gets less positive. So let me start with this. M almost 0. So my y values are going to be almost 0 out here. And then they're going to get more and more positive. And then as you get to 0, they actually end up getting huge. Your slope, your tangent line gets vertical right at 0. So it's almost like having the slope of infinity there. Same thing on this side, almost 0. And then m gets more and more and more and more positive. So this is your derivative. I guess I should have
Wouldn't it go negative on that?
done.
Well,
No.
on the derivative graph.
No, look at this. What's the slope of this line?
Oh, yeah, never mind.
Yeah, so even though you change signs here, the slope actually doesn't change signs. Tricky. I should have graphed this in purple. So here's your derivative. Okay. Does f prime not exist? Now, this is a topic from the first section. So the derivative is always defined as, the derivative at a point x is always defined as this limit. And there are certain times where this limit just cannot exist. So what we're trying to do is characterize which kind of functions or what kind of points on a function will not allow this limit to exist. So there's kind of three problems that you can run into. If a function is discontinuous at all, then the derivative won't exist there. If a function has a sharp turn, the derivative won't exist there. Or if the function has a vertical tangent line, the derivative won't exist. So let's just draw a quick example of each and see if we can reason why the derivative doesn't exist. So there's a bunch of discontinuities and none of them are good. The derivative won't exist in any of them. But let's take a jump, for example. Suppose I gave you this function. Pull here, then it picks back up over here. And I want to decide whether the derivative exists at this x value here. Well, kind of our interpretation of the derivative is that it's the slope of the tangent line. Right? But the thing is, in order for this limit to exist, it has to exist from each side. And it has to, and those one-sided limits have to be the same. So the idea is if you start trying to find the slope of the tangent line by doing successive secant lines here, we take this secant line, and we take this secant line, and we take another secant line, and we try to find the slope of the tangent line, it's going to be different than if we do it on the other side, if we take this guy and we pick points down here. Because of the discontinuity, the secant lines are never going to match up. So the problem with the discontinuity is on the left and right, well, one of the problems, is on the left and right, you're going to get different tangent lines, different slopes of tangent lines. Because you have drastically different y values on the left and right. It's actually the same problem with a sharp turn. Sort of canonical sharp turn graph with absolute value. And if you look at x equals 0 on an absolute value graph, and you try to find secant lines on the right, what's going to be the slope of all the secant lines on the right?
Crossing them.
What's the slope of any of these? What's the slope of those? 1, right? Because it goes up 1 over 1, up 1 over. That's how absolute value works. But then if you take points on the left instead, yeah, then you're going to have slope equal -1. So your derivative can't exist because from the right side of this difference quotient you're getting 1, but on the left side you're getting negative. Another example of this, other than absolute value, is something like, do you guys know another example? Put it on your first quiz, I think.
Oh, the cube root of x squared. Butterfly.
X to the
Or whatever it was.
2/3.
Squared.
Remember this graph? He's got a sharp point at 0. So the derivative won't exist at 0. It's okay anywhere else. Right? I can find the slope of the tangent line anywhere else. But at that sharp turn, actually where I turn around, the slopes are different on both sides. So you won't be able to find the derivative. Vertical tangent line is something like x to the 1/3. Right, on a graph like this, your difference quotient is going to start going to infinity on both sides. Okay? So the limit, we're going to say the derivative doesn't exist as it goes to infinity. As you start picking points closer and closer to 0, you're getting a super steep tangent line. And the closer you get, the steeper it gets. So these are the 3 cases where a derivative can't, 3 easy cases where a derivative can't exist.